the maximal extracted work by unitary, which is called ergotropy. And the amount of energy that cannot be extracted is called passive energy, and the gamma is the corresponding passive state. Okay, the famous example, like I have a Fock state distribution which falls up monotonically with the increasing number of Fock number. And another paradigmatic example is thermal state, which is completely passive. But one can render a passive state into non-passive by measurement. Okay, and if we see talk in terms of B distribution, then for a passive state, it falls off from the origin monotonically and isotropically. So if we have something displaced or the distribution is non-monotonic or falling off anisotropically, then it's non-passive, and we can extract work from this non-passive state by unitary manipulation. Okay. Now this is we start with a input thermal state, so thermal source of light, and we measure this state and see that this state is initially peaked at the origin and falling off isotropically and monotonically. Now if we measure the system, then it got displaced from the origin, and from this displaced state we can extract work by bringing back to the origin. Okay. And if we talk in terms of the optical setup, so we have a high transmittance beam splitter, and we have a source of light, and hello, and due to high transmittance, high transmittivity, most of the light passes through, and we use a tiny part for homodining, which measures its phase like X and P. So these three beam splitter are 50-50 beam splitter, and these four are photo detectors. Okay, so what is happening now? I have the input state, and after measurement, the post measure state is displaced, and here is the optical setup. And we have to use local oscillator for homodining with coherent amplitude beta, and beta is chosen to be real here. And this process is has classical analog. Suppose I have a pendulum. So the optical modes are collection of harmonic oscillator with random phase and random amplitude. So if we think about the classical pendulum and we want to extract work from it, so we have to know its phase and velocity. So when it is in full swing, we have to hold that and release the potential energy as work. So this is the simple screen. So if this is not clear, please stop me and ask any question. So we are just using the same thing. How we stop pendulum. So here we just measure a tiny part, and most of the part remain which is not measured, but it got displayed. And from this non-passive state, we can extract work. Okay. So in the four detector, we have a count N1, N2, N3, N4, and the difference of this gives the information about the phase X and P. Okay. So we can write any input state in terms of coherent basis, and in this basis, any state is diagonal, follows from the seminal work of Dover and Sudarshan. And we have the conditional probability of photo detection delta nx and delta np given the input state in alpha. And if we integrate over alpha, then we get the distribution of the photo count delta nx and delta np. And in this work, we will consider thermal input, but the framework is valid for any state because the treatment is general. And here we show the probability distribution of photo detection for input photon number, mean input photon number n bar equal to 1.55 and n bar equal to 10. So these are all for thermal state. Okay. Now we know the state, and the state post-measure state, which is the unmeasured part, it is displaced from the origin, you can see. Now we need the p distribution, and we can get the p distribution of the post-measure state using Bayes rule from this initial and detected photon number distribution. And suppose we get the outcome delta nx and delta np. So what is the corresponding state? We can have the state if we integrate over all input parameter alpha. So we can see that here for mean photon number, initial mean photon number 10, if we get outcome delta nx equal to 3 and delta np equal to 0, then we have a displaced state. Again, if we consider a state delta nx equal to 4 and delta n equal to -2, we have a displaced state. Okay. And from this, we can see that for the displaced state, the mean quadrature is non-zero. So we can bring it back to the origin where the mean quadratures are 0, and we can extract the work as the potential energy of the harmonic oscillator. And if we average over all out measurement outcome and subtract the local oscillator energy 2 beta square, then we get the average work. So here is the energy balance. We have the input state and we invest some energy in the local oscillators for homodyning. Then the detector absorbs some photon and some energy is lost, and we extract some work by displacement, and the remaining part, which is maybe the passive energy. I'm talking maybe passive because it's not completely passive yet, because there are other possibilities than displacement and also beyond Gaussian unitaries. So this is the remaining energy. And for analytic calculation, we use Gaussian approximation, but we did the exact numerics, and it shows that the extracted work matches with the exact numerics very well. Okay, so here there are two parameters, local oscillator energy and the transmittivity. So the work extracted by displacement, we can optimize over these two parameters. And if we optimize, then we see that we get work when the initial mean photon number is greater than 1 from this expression. And this optimized value we get for when the local oscillator energy is square root of bar n, so it is the square root of the input energy, and when the transmittivity kappa is of the order of 1 minus kappa is order of 1 over square root of n. Now we can simplify this expression for high temperature, and we get the work n bar minus 4 square root of n. So this 4 square root of n, the lost energy of the initial energy bar n, is due to the detector absorbs square root of n number of photon, and we invest square root of n bar energy in the local oscillator, and 2 square root of n is the remaining energy. So that cannot be extracted unitarily. Okay. Now here we have talked only about displacement, but what about other possible? So we cannot perform these Gaussian unitaries other than the Gaussian unitaries, which are difficult to implement experimentally, but we can do squeezing. So, but what we have seen that the amount of work that can be extracted by squeezing is reduced in the amount when we increase the mean number of photon. So the amount of work compared to the displacement is significant for n bar equal to 2. But when you go for large photon numbers, it is insignificant compared to the work extracted by displacement. So here is the advantage of this protocol, that we can extract the work by only one unitary, and which is displacement. Okay, so till now I have considered only ideal cases, but what about noise? So there can be thermal noise in the unused port or the empty ports. So, and also in the homodynamic setup, and there can be inefficiency in the detector. So, okay, so this inefficiency of the detector we can model by another beam splitter, which is highly transmit according depending on the detector efficiency. So most of the photon passes and some reflected. So the reflected photons do not appear in the detector. So and also, like, if there is thermal noise, and we can get dark counts. So we are considering all kind of possible noise, and we are seeing that this blue line represent the ideal case when there is no noise, and the green three green lines that represent the noisy case. So we took the detector efficiency 0.95 to 0.5 and the detector temperature 0.01 to 0.1. And we can see that when the detector efficiency is half and the noise, the detector temperature is also very high, then also for large photon number, we can approach unit efficiency. And we have also considered, because it is a measurement engine, we have to also consider the Landauer erasing cost, and the red lines represent the erasing cost. So we can see that considering all noise and erasing cost, it can approach the unit efficiency when we have a thermal source with mean photon number 10 to the power 4 and of this order. Okay. Now we compare with other photonic Maxwell demons. So here's a very nice work by Mihaly Csikszentmihalyi et al. And they have proposed a photonic Maxwell demon. And here the efficiency is bounded by 1/3. So we'd like to highlight that the main reason that we get high efficiency because we are using a tiny portion for measurement. So we can use a tiny portion for measurement, but still we can get enough information which can be feed forwarded to extract almost entire amount of the work. Okay, so despite we get in-bit efficiency, it's not violating Carnot. So I'm not going into the details. And we compared with paradigmatic heat engine, stroke engine. So our scheme, this WA, can be 4 times powerful than the auto engine. So, and the reason that we get high efficiency than other measurement engine because we are using a tiny part. So this is the novelty of this work. Okay. Now I will discuss about coarse graining. So earlier I have assumed that we can detect delta NX and delta NP exactly. But what about we have like the resolution of the detector is not so good. So they're counting 5 photons and showing say 3 or 2 or something. But for analytic calculation, we consider a extreme coarse grain situation where we are only know that whether delta NX or delta NP is either positive or negative. So we have 4 possibility. And we represent these possibilities as like plus plus when delta NX and delta NP plus and so on. And what we got, like we again optimize over the local oscillator energy and transmittivity. And we get in the high temperature that we get in the leading order, the work is reduced by 1/2 pi. So when we don't have the information, exact information of delta NX and delta NP, so the work is reduced. And if we don't have any information of delta NX and delta NP, so there is no work extraction possible because by beam splitter we are measuring and we are not feed forwarding, though then the post measure state also is thermal in nature. So the information we acquire is very important, though we are measuring a tiny part. Okay, so what about photo count? So what we can do that I have a thermal source of light, I can do quantum non-demolition measurement, and suppose we got some Fox state and I can extract the energy, but non-demolition measurement is difficult and we have a reasoning cost. So again, we apply the small fraction photo count. So you have a high transmittance beam splitter, most of the part is transmitted and small part is used for photo detection, photo count. Suppose we detect M photon with probability PM, then we have the corresponding post-measure state and it has energy EM. So what is the nature of this post-measure state? So see, the green line represents the initial thermal state and which mean photon number 20 for all these cases. And suppose we detect a 1 photon and the corresponding post-measure state is non-monotonic. So we can see that this is not passive. And similarly, if we detect 10 photons, the corresponding state is non-passive. But one thing, if we see the phase-phase distribution, it is centered at the origin and it is isotropic, but it does not fall monotonically. So there is a crater in the hollow crater in the middle. But we cannot extract work from this by squeezing or displacement. So what we can do, like from the post-phasor state, we can do permutation in the Fox basis, which is obviously experimentally difficult, but we can extract work from this post-phasor state EM with energy EM, and by permutation we can reduce this energy, and we can get the average work if we average over the outcome probability PM. Now we compare photo count and homodynamic. See, for low photon number, the result of photo count is better because there we don't have to invest local oscillator energy for homodynamic. But when we go to the high photon numbers or 10, even 10 photons, then we see that we get more work by homodynamic and it is experimentally more feasible because we only need to do displacement, which is easier than permutation in the fog basis. And the efficiency increases, the gap increases for high photon number. Okay. Now I'll talk like how much information we gain. So suppose my input was in a particular state N and we got the measurement outcome M, then the point was mutual information given by IML. Now, if I integrate over all input distribution and outcome, then we get the total mutual information gain. And the mutual information we get, which needs to be feed forwarded for work extraction. So the feed forward cost, which is very much technical and setup dependent, but it has a lower bound. And we calculate the lower bound, and this red and green and blue represent, this is for homodyne, small fraction homodyne, this is for small fraction photo count, and this is for coarse grain homodyne. So we can see that the feed forward cost or the lower bound of the feed forward cost or erasing cost is not that much. And however, if the cost is high also, then we can increase the number of input photon, and we can always reach to the unit efficiency. Okay. Till now I was talking about measurement, but I have to compare its efficiency with the reversible one, which is the most efficient method for work extraction. So suppose I have a thermal field which has mean quanta n bar, and I have I'm using auxiliary system n-1 folder mode with NC bar quanta on average, and I will do this reversibly. So I'll preserve the entropy, so that if I equate the entropy, initial entropy and final entropy, then I can extract work by reducing the energy. So pictorially, suppose I have a cold mode with mean photon number NC, which is taken 1, and I have a hot mode with mean photon number 20, and these two modes combine to represent the point C. So if I don't change its entropy, but if I can reduce its energy, then I can extract some work. Okay, and instead of 1 cold mode, if I take 4 cold mode, then I can extract even more work. So for 4 cold mode, I can extract 13.9 quanta out of 20 quanta, and for 2 cold modes, I can extract 11 quanta out of 20. Okay, so but how to do it? So here we can show this graphically by 2 modes. So suppose I have a hot mode with mean quanta n bar, and I have a cold mode with mean quanta nc. So first we adiabatically, what we do, we increase the frequency of the cold mode, and we decrease the frequency of the hot mode, so that they belongs to one isotherm. So blue dashed line represent isotherm. Okay, so in this process, the hot mode releases some energy, which is informed work because there is no entropy change, and the mode and we have calculated the work, and the efficiency is given by hello. The efficiency is given, there is additional factor apart from Carnot, and this factor arises due to finite number of modes, because when you have a heat bath, they have infinite number of modes. So this is the correction due to finite number of modes. Now here we plot with suppose we have total number modes 2 and 5, and the hot mode, number of hot mode is 1, and rest are cold modes. So for infinite number of cold modes, we can reach almost unit efficiency. Now we can see that homodyning approaches the reversible one when we go for high photon number. Okay. Now I'll discuss. So we have proposed a new scheme for work extraction by measuring a tiny parts of thermal light source. And these schemes can be used for any other continuous variable, so beam of atoms also. And it is superior than previously proposed information engine and auto engine. In the classical limit, this can reach the efficiency 1 minus 10 to the power minus 17. And also, like, as it is approaching the maximum efficiency, unit efficiency, so it approaches the reversible. And what we have seen, that homodyning is better than photo count. So it is better in terms of efficiency and better in terms of experimental feasibility. So the Weizmann in optical groups, we are also in the process of realizing this experimentally, and hopefully we'll get some result very soon. Okay, so thank you for your attention, and any question, please feel free to ask.
Thank you, Dr. Mishra, for this exciting talk. The floor is open for question now. Yeah, Professor Panigrahi, please go ahead.
Yeah, Avijit, what kind of
Yes,
experiment you are
please.
thinking about?
Okay, so like we are talking with Ofer Fastenberg, and suppose they can generate a thermal light source, and we have suppose highly transmitted beam splitter, and we measure, we like do photo detection. So delta nx and delta np, and then we have the post meter state, and we can do the displacement. But displacement we can do by again a beam splitter. But here, like the main catch or the main challenge of the experiment is we need to a beam splitter with variable transmittivity, because depending on the delta nx and delta np, we need to change the beam splitter transmittivity.
Correct.
And using a transmitter, we can realize the displacement operator.
Yeah.
So, like what we are proposing theoretically, we are exactly trying to do this.
Very nice talk. Enjoyed. Thank you.
Thank you, Professor Panigrahi. Any other question? Okay, if not, I have a very short one question. Means place you have mentioned that you are dealing with all kind of noises, not only white noise. So that means you are taking care of the colored noise also.
Yes.
Okay.
What this setup is general. So what is the possibility of noise? So I have empty ports. So I am working in an environment and there can be thermal noise, right?
Yeah.
So it's entering, and we need to know like the mean photon number, and it can enter here also. And suppose we have local oscillator, we assume this is like coherent, but in general it cannot be coherent. It can be an mixed state. So and what we are doing, like we are working in coherent basis, so we can treat any state. But here for the plots we are treating thermal. And the detector, there is noise. The detector is not efficient, or we have like coarse graining, or we can have dark count. So the dark count we can model. Like there is a thermal source, and this photon, like one photon from this thermal noise source or any noise source, is coming, and after reflection it goes and gives a dark count. So we are considering this kind of noise.
Okay. Thank you very much. Thank you. Any other question? If not, let's thank the speaker again, and we move to the next speaker, who is
thank you for this opportunity.
Yeah, thank you very much for this exciting talk. Our next speaker is Mr. Amit Anand, and I request Mr. Anand to switch on his camera. Yeah, hi, welcome, Mr. Amit Anand. So he did BTech from IIEST Shibpur, and now currently he is doing masters in Institute of Quantum Computing in University of Waterloo. So let us welcome him, and kindly share your screen, and please start your talk.
Hello, my name is Amit. Thank you for giving this chance to talk for a talk. So today I will be speaking on quantum chaos. This is my field of research for my master thesis. And yes. So in this first I'll give a brief description about the classical chaos theory, and then what are the limitations of that while studying the quantum chaos. And then I will introduce a model that most of the people use as a quantum kickdog model to study the quantum chaos. So the classical chaos theory was first, this chaos theory was first proposed in 1880 by Henry Poincaré when he was studying three-body problems. And he found that for this three-body system, there was some non-periodic behavior which neither goes to infinity or it doesn't go to any fixed point. But after that, there was not much work done in this field. And from 1880 to 1950, 1960, these people did some work, but most of the work was motivated to the physics, not the proper mathematics point of view. and to solve some linear, non-linear system, and etc. But the main breakthrough came in 1960s when the use of electronic computer was there. They started to do simulations on the computer, and the data were more precise and accurate than what they could do with the hand. And in 1961, Edward Lorenz, when he was working on his weather prediction model, he is one of the pioneer of the classical chaos theory. And he noticed that by changing the data by a very small amount, there's a huge difference in the outcome of the model. So that was like an accidental breakthrough, but later on, like it was developed with this. From here, it was developed to a very good theory. So the properties of chaotic system are like these three here. So first, they are aperiodic for a long time. They are deterministic in nature. That means for a given initial value, there will be some fixed outcome. And they are very sensitive to the initial condition. Like if we perturb it little bit, then there will be a huge difference in the outcome, and which was given by this Lipnoff exponent. So here you can see this delta ZT is the difference in, let's say, position for any time for two closely initial point, and delta Z naught is the initial difference in the position. So if the difference in the initial position grows exponentially with the time, then we call that system is chaotic, and that is parameterized by this lambda term here, which is not a Lipnoff constant. So this is one of the way to say that, okay, the system is chaotic. So the limitation of this theory in a quantum system is that we are not able to measure the position of the particle or anything in very accurately because of this Heisenberg uncertainty principle. And the second problem is that we do not have anything as non-linear in quantum mechanics. Everything is linear. And for the classical chaos theory, we need the non-linearity in our system to behave it as a chaos. So these are the problems that we face while studying the chaos in a quantum system. So to remove this, what we do is that we study a system that is chaotic in a classical limit. And so we study that kind of model by doing this quantum evolution, and we look for the signatures of the classical chaos in a quantum system. So there are many signatures of chaos. I'll just discuss these three. So the fidelity decay is one of the signatures where a state is evolved with some Hamiltonian H0 and then some perturbed Hamiltonian H prime. And then we calculate the fidelity between the states evolved with these two Hamiltonian, and we see whether it is increasing or decreasing. It was proposed that if it is decreasing, then it has to be chaotic. But it is not a very good measure or very good signature of a chaos because there are models which are not chaotic, but it still show this decreased tendency. The other signatures are OT-OC correlators. That again, it's a very good signature, and it is being used in many different models nowadays. The third one is the entanglement. That is a signature of a chaos, and this is what I will discuss in this work. So the model that I am working with is known as a quantum tick-tock model, and this model is a finite dimensional model where the total spin is given by this J value, and it was first introduced by Harke, Kosinskov in 1987. The Hamiltonian of the model looks like this. So it has two parts. One is this is a linear part where the rotation is given in along JY direction, and the rotation value is given by this P. So depending upon this V value, we will rotate the system, where tau is the time period. Now, the first part of this Hamiltonian is non-linear in Z direction. Now you can see the strength of this non-linearity is given by this kappa. And this part of this Hamiltonian only kicks in at a fixed interval of time that is given by this delta function. So after every end of the period, we are kicking this part of the Hamiltonian. So this is something like a kick non-linear twist that we are giving to the system. Now the benefit of this model is that this model behaves as a chaotic model in classical limit when we take J to be infinite. So we study this model for the quantum chaos. So classical dynamics looks something like this here: x naught, y naught, and z naught. And for where x is given by jx by z, y is given by the jy by z, and z is given by zz by z. And by integrating this classical equation, we get the stroboscopic equation. And for this case, we are assuming tau to be 1, time period to be 1, and t to be pi by 2. And for the rest of the talk, we will assume that. So you can see that since this equation, we can, and the other thing is that x square, y square, and z square is always equal to 1. It is always normalized. So we can study this on the sphere of radius x square, y square, and z square. And then we parameterize this x, y, and z with theta and phi. And this is how the classical dynamics looks like. So these are the different, here we are taking p to be equal to pi by 2 and tau equal to 1. And for different values of kappa, we are plotting the classical phase space. I'll explain this plot a little bit. The first one that you are looking at for kappa equal to 1. So in a phase space, for different thetas and phi, we are taking an initial point, spin coherent state. And then, for different theta and phi, we are taking a state, and we're evolving with the classical dynamics, classical equation of motion for 200 kicks. And then we are tracking the trajectory. So here you can see that we get a global picture for, and we are doing this for the different values of kappa. So you can see that for the lower values of kappa, such as kappa equal to 1, most of the phase space is dominated by the regular trajectories. So these points are the regular trajectories here, and these are the chaotic points. But as we increase the kappa, the transition from the regular to chaotic phase space takes place, and these islands get the bifurcation of these islands takes place, and you can see this bifurcation here. This bifurcation takes place something around 2.2. And this, and as we keep on increasing the kappa values, these islands are the regular islands. These regular islands become smaller and smaller, and the phase space is mainly dominated by the chaotic C. And for 4.0, you can see this is very small. Now, the other feature of these classical points, classical phase space, are these points that you are looking at, pi by 2 and this pi by 2 minus pi by 2. These are known as a fixed point. It doesn't move if you start at this point, and these points are known as the period 4 points. This curve that you are looking here, this curve, and this point is also a period 4 point. So what we do study is that we study these points, these special points, and we try to reconstruct this classical phase space in quantum case. So that was about the classical evolution. So in quantum evolution, what we do is that we evolve the Hamiltonian just for one time period. We write what is the unitary for that. We get something of this kind, and this part is the strength of this kick is given by this kappa parameter, and the rotation is given by p. When we get this unitary for one kick, we use this unitary again and again to get for any number of kicks or for any time. So applying this unitary again and again, we get for n kicks. Now what we do is that we model this system in a qubit basis. Since at G squared is the constant of motion, so total angular momentum is conserved here. So we represent this as a n equal to 2j qubit states, and it always lies on a symmetric subspace of a 2j qubits. So total dimension of the Hilbert space is not 2 to the power n, but it is 2j plus 1 cross 2j plus 1. And we start with the symmetric state, and we always end up with the symmetric state. And this Jx, Jy, Jz that I showed before is written in terms of Pauli matrix. So when we write the Hamiltonian in a qubit basis, it looks something like this here. So these are the single qubit operations, which is given by this P, and this part that is a non-linear part in the actual Hamiltonian turns out to be the correlation terms in the qubit picture. So what we do here is that we start with the spin coherent state. The reason for starting with a spin coherent state is that it has minimal uncertainty principle, and also we are looking at the entanglement, how the entanglement evolves in time. So these states have zero entanglement initially. So whatever entanglement gets in the system is because of this evolution. So which looks like something like this. This is a Yosemite distribution of any spin coherent state, which is centered at theta and phi pi by 2 minus pi by 2. And you can see that as you increase the value of j, you're going more and more closer to the classical picture. So for j equal to 4, that is 8 qubit, it is somehow spreaded in the phase space. But if you go for j equal to 50, which is here, then you can see it becomes more and more point-like structure. And if I take j to be infinite, it will be a dot on the phase space, which will exactly replicate the classical point. So this is one of the results, theoretical results that I took from 2004 paper. And here the idea was to show that different points in the phase space, classical phase space, will behave differently when you will evolve with the quantum Hamiltonian or unitary operator that I showed before. So here you will notice that this is a classical phase space for kappa equal to 3, and for kappa equal to 3 we get a mixed kind of phase space where we have some regular points and we have also the chaotic points. So if you will see that if you fix the theta 2.25 and you cross out of this island here, then you will see these points are the regular points, these are the edge of the chaos, and then slowly you are entering in a chaotic scene. So this part was the lower plot is for 500 qubits, and here you can see this theta is 2.25 and phi is 0.63. That means at the center of this island. So for that, the linear entropy, it always remains lower, close to 0. But as we go out of this point, something around this region, phi equal to 0.9, there is some entanglement generation in that state. And as we are going out, 1.05 is the edge of the chaos. Phi 1.05 is the edge of the chaos. And for this, there is a more entanglement. But as we are going phi equal to 2, that is 2.25 and phi equal to 2, something here, which is deep in a chaotic scene, you can see how quickly the entanglement rises and then it saturates to its maximum value. Not 1, but the maximum value for that given point. So that is the idea to show here is that the chaotic point will have the more entanglement and generation over the time, and the regular points or the fixed points will have low entanglement. And that you can see for this is the case for the 50 qubits, but here it is not very clear to see that one. But as we are increasing the number of qubits, we are going into more and more classical picture, or this is semi-classical design. So there are some experimental studies as well, and this was the first experimental implementation of this model, and it was done in 2009. And in this one, they use a cesium atom to represent the qubit, and It was done with a 6 qubit. And the second experiment was done by the Google group, and it was done in 2016. And in this one, it was done with the 3 qubits, and they studied the ergodic dynamics and the thermalization in this chaotic model. The other experiment was done by these people, via Kartika and al. This was done with using the NMR qubit architecture. And this was done with a 2 qubit. In all the experiments, they had shown that even in a deep quantum regime, you can have the subsignature of the classical phase space or classical chaos. So what we did is that we implemented this model on the IBM Open Quantum Computer for 2 qubit, that is J equal to 1. And for J equal to 1, the Hamiltonian looks something like this, where this is the qubit to qubit interaction, that this is responsible for creating a correlation or entanglement in the system. And this is a single flip operations, single qubit operations, this two. And the corresponding unitary operator is given by this. Now what we did that we started with a spin coherent state, that is both the qubit have same initial parameters. We evolved that using the unitary kick we derived for 1 kick, unitary operation derived for 1 kick for n number of times. And then evolving schematics is taken, it was obtained using the tomography. And then we calculated different parameters such as concurrence, entanglement, or whatever you can calculate from there. So the implementation was something like this. Like this is my total operator, that is 2 for 1 key. And this can be decomposed into single qubit or control unitary in this form. Now, this is a paper which mentions how to decompose this kind of unitary, where any unitary of n size can be decomposed into n minus 1 by 2 single qubit and a control unitary case. But this single unitary and a control unitary cannot be directly implemented on the IBM. So the further decomposition is required, and that each U1, U2, or 2U6 is further decomposed into the rotations and the C0 case, which can be directly implemented on the IBM. And you can see this is like U1, U2, U3, U4, U5, and then U6. So this is how we implement it. The benefit of this method is that in the previous experiment, it was very difficult to have high interaction, like high values of kappa, because as we are increasing the kappa value, we are increasing the qubit to qubit interaction, which is very difficult to handle in this kind of architecture. The second problem was that as they are increasing the number of kicks, the fidelity drops very quickly. So after 20 or 30 kicks, it is not possible to see anything there. The fidelity drops to less than 0.5 or something like that. But by using this method, whatever number of kicks you want, you just have to change the parameter for these gates. You do not need to change the number of gates that we are using. So whatever error that we have for the 1 kick, it will remain constant for any number of kicks. And that you can see here. So this is the fidelity plot. Now these are the different values of kappa and a theta and phi that we have taken. And this is the fidelity between the density matrix that we obtained after tomography from the actual IBM quantum computer and the theoretical density matrix that we calculated. And you can see here that the fidelity remains very close to 0.87. The small differences that you can see is because of the intrinsic noise. But other than that, as a function of kick, it doesn't drop out. It will remain at the same level. So ideally, we can do any number of kicks and we can see for a longer time period what is the behavior. So we did calculated the concurrence for that. And you can see here, this is the plot that is taken from the IBM simulator. And this was done for different values of kappa. So on x-axis, you can see there's a kappa value, and on y-axis, there is a number of kicks or the time parameter. And you can see we started with only one SCS state, that is theta 2.25 and phi 2.0. And you can see that there is a periodicity, some periodic behavior in kappa. And this was also there in the other paper as well. All the theoretical papers, you will see that this any quantum correlation that we calculate from here will be a periodic in nature. And that periodicity is given by kappa equal to 2j pi. So for us, it is j equal to 1. So we are getting periodicity at 2 pi. And there is also a temporal periodicity, which is something around 25 kicks. Now this plot is taken, this is the same thing, but it is taken from the real quantum hardware, that is IBM Vigo. And here also you can clearly see the periodicity to be 2 pi and temporal periodicity to be 25 kicks. Now here what you are seeing is that this is the classical phase space for kappa 2.5. And in this one, we took 289 initial points, and then we evolve it for 200 kicks using the classical equation to get this global picture of the classical phase space. Now on the second plot, the middle one, what you're looking at is we still took 289 initial spin coherent state. We evolve it for the 200 kicks using the unitary operation. And then we calculated the time average in time concurrence. And that we plotted on the z-axis, and then we took the contour plot. Now this was done on the IBM simulator, and the third one that you are looking at was done on the IBM real hardware, like actual quantum computer. And you can see the classical phase space is very accurately represented using the concurrence, time average concurrence plot. And you can, in the real hardware also, you can see this, all these islands that you are looking here is clearly visible. These are the period 4 points, and you can see that the state which are localized in this region, the islands, have low entanglement, low concurrence value, and the states which are in chaotic has a somewhat intermediate values. But the points which are like high, this period 4 points have the maximum, maximum time average concurrence value. So this was our results, and the most important part of this is that we can exactly see the classical phase space. All the features of the classical phase space is replicated here. And the second important thing is that this is done for the 2-qubit system, which is the smallest possible system that we can see, which we can use to study any kind of interaction or the chaos. And it still represents this much of signature for the something which is a classical behavior, such as a chaos. So yeah, that was it. Thank you.
Thank you very much for this exciting talk. It's huge volume of work in your master's thesis, I must say. The great amount of work. So the floor is now open for question. Any question? Please feel free to ask your question.
Yeah, I have a small question.
Yes.
See, I'm actually very curious about this, phase space, the origin of this periodic orbit, because it is going to throw light on the bound state problems. What is it that these periodic orbits slowly emerge? In B, they are evident. In C, they are more amplified. What is the origin?
What is?
What could be the, basically the origin of this periodic orbit?
Oh, this is periodic orbits. It depends upon the initial points. Like these points are just like it just oscillates between certain. In the classical picture, it just jumps from 3 or 4 points. It doesn't behave as a chaotic manner as these points are.
Okay. Very interesting. Thanks.
Thank you.
Thank you. Thank you, Professor Panigrahi.
Thank you.
So any other question? Okay, if there is no further question, then let's thank Amit for this fantastic work presenting it here. And we move to the next speaker, which is Soumik Mahanti. So I request Mr. Mahanti to.
Am I audible?
Yeah, you are audible. So Soumik Mahanti did masters from IISER Kolkata and now currently working as a project student there. So I request Mr. Mahanti to please share his screen and switch on his camera. Thank you.
Okay. I think, may I present without the camera, because I think my network connection is not too strong.
Okay, fine. Please go ahead.
Okay, thank you. Thank you, sir, for your kind introduction. Let me share my screen. Excuse me.
Yeah, please. So we cannot yet see your screen. Screen, I think it is still loading. Yes, Soumik. I think there is some network issue, so I request the audience to please keep patience.